So today is part 3 of a 3-part video lecture on solubility and colligative properties. The other 2 videos can also be found on YouTube. And today what we're going to really focus on is the quantitative formulas we can use to determine how dissolving something in a solvent will change the properties of that solvent. So let's start with boiling point. When you dissolve a solute in a solvent, it will change the boiling point according to this formula, which shows that the change in temperature away from the original boiling point can be determined if you know this constant. It's called the Molal boiling point elevation constant, and it is specific for the solvent, not the solute, times the molality of the solution. And just a hand-waving explanation of why this happens, remember that when you dissolve something in a solvent, the solute is actually taking away energy from the solvent molecules. So those solvent molecules that have enough energy to boil are actually bumping into the solute and losing some of their energy. So it requires more energy to make those boil. And the important measure that we learned in the last video here is molality. Now, so one other point I want to leave you with here is make sure you compare the type of things you're dissolving. Here I'm dissolving glycerol, sodium chloride, calcium chloride, and iron 3 hydroxide. And I'm going to put a glycerol molecule up just so you can see its structure. It's a single molecule that when it dissolves, it doesn't disassociate. It bonds through hydrogen bonding, all these different alcohol groups, hydrogen bond to water. And this is fairly miscible with water. You can put any amount you want in water and it will dissolve. Whereas with salts, you usually have a lot more water than you do have salt. So when you do the calculation for molality, one caution is if you were to use 1 molar glycerol solution, you prepared it such that it was 1 mole of glycerol, that would free up 1 mole of solute, the critical amount that would determine this formula. But if you dissolve 1 mole of sodium chloride in a kilogram of water, it would actually free up 2 ions, a sodium ion and a chloride ion, so it would be 2 molal for this calculation. And calcium chloride would free up 3 ions for every calcium chloride that dissolves. So a 1 molar solution prepared, 1 mole of calcium chloride dissolved would actually be 3 moles per kilogram of solvent. And then just another caution, when you take a material like iron 3 hydroxide, remember from your solubility rules, it's insoluble. So it would not dissolve, and because it's not dissolved, it actually doesn't influence the colligative properties very much. And so without determining exactly, we're just saying, generally speaking, there's very little concentration that's in solution. Freezing point depression, the formula looks very similar. The only difference is you pick a different constant. This is the molal freezing point depression constant. And in this case, the temperature is always driven down. And just a hand-waving explanation again, the colligative property results from the solutes disrupting the orderly binding of solvent molecules. So you got to slow down both the solute and solvent to get it settled down enough or slow enough kinetically that the molecules can set to bind into organized lattice. Freezing point is proportional again to molality. Here's a chart that shows the constants for different solvents. And once again, when you pick constant, it's related to the solvent, not what you're dissolving. So in all those examples I gave you, the calcium chloride, the iron 3 hydroxide, the sodium chloride, the glycerol, all of those were dissolved in water. So you would actually pick constants for water. So let's do some calculations here. Compare the change in boiling point and freezing point of a 1 molal glycerol solution in water versus a 1 molal calcium chloride solution in water. So here we go for the glycerol calculation. Remember what you do is take your constant times the molality, and these are both 1 molal. The constant is for water, and in this case we're doing the boiling point, so we choose the boiling point constant, 512, change in Celsius per molal. Work that out, it's pretty easy. It's 0.512 C. The sign on this is what should be assigned logically, knowing that because you're dealing with boiling point, it will always go up, so it's always positive. So the new boiling point of water starts at the original boiling point plus the change, so it's 100.5 degrees C. Freezing point, the only difference is you choose a new constant, 1.86, still a 1 molal solution. Now the temperature change is 1.86 degrees C, but because it's freezing point, it's a depression, so it goes below the original freezing point, which is 0, 1.86 degrees Celsius below zero. So now let's go over and do the calcium chloride solution. Use the same constant because it's still water, same solvent. Now it's 3 molar because remember, 1 calcium chloride actually breaks up into 1 calcium ion and 2 chloride ions. That's 3 equivalents. And if you do that calculation, it's a much larger change. So the temperature raises 101.5 degrees Celsius. Always raising. Freezing point depression, same general procedure. Now this is 5.58 degrees C, but because it's freezing, we want to do a depression. We want to subtract it from the original freezing point. So how much glycerol? What if you're working the other way around? What if you needed to change it to a certain temperature? So how much glycerol? It has to be added to 225 mils of water to raise its boiling point to 107 degrees C. So we start with this formula, and the change in temperature is from the original 100 to 107, so that's 7 degrees C. The constant is still the same because it's for water. And then all we have to do is figure out the molality of the solution. Solve for M. So if you work that through, M equals 13.7 molal solution, which means 13.7 moles for every 1,000 mils of water. But we don't really have 1,000 mils of water. We have 225 mils of water. Multiply that by the 225 mils. That'll cancel out the mils. You get 3.08 moles of solute that have to be added to this 225 mils to make it a 13.7 molal solution. So let's work our way through this math. You have 3.08 moles of glycerol is what I need to deliver. Well, glycerol is liquid form, so we have to get this into some sort of volume to dispense it, or we could dispense it on a scale. Just to remind you where this came from, if you get C3H8O3 and you went on your periodic table at 12 grams per mole for carbon, 3 of those, and 1.008 grams per mole for hydrogen, 8 of those, and 16 grams per mole of oxygen times 3. That's where that number came from. Multiply by the molecular weight, that'll cancel out the moles. Now you divide by the density, that'll give you to mils. So basically you have to add 225 mils in order to change it 7 degrees. Now I did this on purpose because it happens to be 1-to-1. It's a 50% volume per volume solution, and it would raise the temperature by 7 degrees C. Now if you could quickly turn around and say, well, how much would that change the freezing point? This might be a good antifreeze for your car. Now if you did the same calculation, all you need is the molality times the constant. So here's the molality that we've already figured that. There's the constant. You multiply them together. It'll actually change it 25 degrees, so it goes 25 degrees below zero. So that's a fairly significant change here. This may not quite get the job done. In your car, though, you're really concerned about freezing, and the way you control the temperature is not just the antifreeze, you also put it under pressure, and as you raise the pressure in the headspace, it actually raises the boiling point considerably. And that's even a more effective way to prevent it from boiling. But the truth of the matter is that you don't usually use glycerol because it's fairly toxic to the environment. So they use a material called ethylene glycol. But you can see the same sort of properties exist. It's highly polar, so it's miscible with water. Nothing really changes. You would still mix it in the same proportion, so it's 13.7 molar. And this is a fairly common volume to volume percent that you would mix antifreeze in. You don't go much above these volume ratios because you start to lose the specific heat capacity and viscosity, low viscosity qualities that water adds to the mixture. The 13.7 molal solution changed the boiling point to 107 degrees C. What if you didn't want to use ethylene glycol? What if you want to use something that's cheaper, like table salt, sodium chloride? How much sodium chloride would you have to add to get the same result? Once again, I remind you that sodium chloride is not a one-to-one relationship. When it dissolves, it creates 2 equivalents. So if I took the 13.7 molal that I'm trying to achieve, and I use a stoichiometry that says, hey, look, there's 2 molal of ions for every 1 molal of sodium chloride dissolved. That would say I really need to make a 6.85 molal sodium chloride solution. All right, so 6.85 molal sodium chloride is 6.85 moles in 1,000 mils of water. We're really only doing it in 225 mils of solution. There's a molecular weight of sodium chloride from the periodic table. 90.1 grams of sodium chloride is all I need to dissolve. So if I could dissolve 90.1 grams of sodium chloride in that 225 mils of water, it would have the same effect. But here's a fact that sodium chloride is not miscible. It actually dissolves because the strong ionic bonding is outnumbered by the polar water. So it takes a lot more water than it does sodium chloride to dissolve it. And it's not exactly 3, it's a little less than 3, but basically it takes about 3 grams of water for every gram of sodium chloride to dissolve. And that's quite a few moles more, because water has less grams per mole. So if this fact is accurate, is this scenario reasonable? So let's work our way back. We got 225 mils or grams of water. So if we just use this quick 3-to-1 ratio and we divided that by 3, we could dissolve up to 75 grams of sodium chloride. Well, unfortunately, we would need to dissolve 90 to achieve that minus 25 degree drop in temperature. So no, the limit of colligative properties, and this is the reason I did this experiment, is just to remind you, if you're trying to use colligative properties in your future engineering days, the limit sometimes is just the solubility of the material. And that's why they choose things like ethylene glycol and glycerol for some applications, but in other applications, maybe you favor the ions. And for example, if you're worried about conductivity, ethylene glycol and glycerol are a no-go. All right, let's move on. Now we're going to work on a problem just calculating the molecular weight of macromolecules. But the reason I've chosen this problem is because I want to introduce you to osmotic pressure, the actual calculation for it. And osmotic pressure has this funny little Greek symbol. And to calculate it, you basically, if you look at this, it looks a lot like the universal gas law pressure calculation, which says if you had to find the pressure of a gas exerted, right, it would be nRT over V. So it's very similar in this sense because we're creating a pressure by putting an imbalance in particles in here. And so what's the pressure that the fluid exerts in all directions? But this might help you remember this formula. N, that's the number of moles. V is the volume of the solution. Now this is different. This is not the volume of the solvent. It's actually the volume of the solution total. And if I knew the number of moles and the total volume of the solution, that looks familiar. That's actually molarity. So you could rewrite the osmotic pressure formula. You can use it in either form. Molarity times RT. And in this case, it's appropriate to use the R of 0.0821 liters atmosphere per kmol because it has a pressure unit in it. And you're trying to solve for pressure. And if you use this constant, it should also remind you that, look, if I'm going to use temperature, it should be in Kelvin. If I do use this expanded form, and I'm looking for the volume, should be in liters. So let's work a problem here. All right, so we retrofit this tube and we actually put a pressure gauge up here. So as the pressure starts to build and push, you're going to actually just read it here and the water level isn't going to change. So, and this is also calibrated so we know the water level in this side of the chamber. Then we're going to drop a temperature in there, and I just chose to put the thermometer on this side, but it should be fairly consistent throughout. So in this case, you could, if it's a solid macromolecule, you could weigh it beforehand. So for our example, we have 21.5 milligrams of material. So we dissolve it in there. Water starts coming in. Only now the water volume doesn't change because we have this capped off and the pressure gauge is in place. And now we just read the raise in pressure. So that generates 4.75 e to the minus 3 atmospheres. And that probably would be accurately measured in torr, but we've already gone ahead and made the conversion. Go over to the other side, read the temperature, 278.15 K, about 20 C. There's the volume. You can look on there and see that the volume is about 1.5 mils. So now we actually have all the pieces of the puzzle. Okay, we got it off the gauge. Pressure equals. We're going to solve for molarity. We have the universal gas law constant. Put liters atmosphere over kmol. And then we find the temperature, 278.15 degrees Kelvin, 20 degrees Celsius. Sulfur M, which basically says you have 2.08 e to the minus 4 molarity, or moles per liter. So now I'm going to work my way back to molecular weight. So that's how many moles per liter, but I only had 1.5 mils, which is 1.5 e to the minus 3 liters. So if I multiply these together, the liters should fall out and I should have the number of moles I've got in there. And molecular weight is grams per mole, and I happen to know the number of grams I dropped in there. So this is very reasonable to do all these measurements. I convert that to grams, and now I have grams per mole. Just simplify it down. It's 6.89 times 10 to the 4th grams per mole. So this is a large macromolecule, some sort of protein type size. But there's a way that you can calculate the molecular weight of a material. And by way of that, I've introduced osmotic pressure formula to actually quantitate exactly osmotic pressure or some component of this formula, which could be molarity or it could be moles per volume. Another application or calculation is with vapor pressure changes. And as I've talked to you before in the last videos, if you take something that isn't volatile itself, the vapor pressure change is only going to be to the solvent if it has some vapor pressure to it. And the vapor pressure will drop off because, once again, some of the energy is tied up and bouncing around with this solute. On the other hand, if you put a solute in there that it also has a little vapor pressure, then both of these molecules are going to change the vapor pressure of the other. And that'll make even better sense when we do the calculation. So the actual calculation is based on Rouault's law, which basically says, look, the vapor pressure of the solvent is determined by the molar ratio of the solvent times the original vapor pressure of just pure solvent alone. So you'd have to know this number. And these are available in many tables. I like to rewrite this a little differently though, because this works best if you have something like this, where basically whatever you're dissolving has no influence on the vapor pressure, but this one basically will tell you partial pressures for all the components. So it can be used for either situation, and it basically says if you want to know the partial pressure of each component, figure out the mole fraction of the component times pure vapor pressure of the component without anything mixed in. So let's apply this. Let's use the exact example from we'd done earlier where we'd put 50% volume per volume glycerol and water. And let's figure out the vapor pressure of the water. So that calculation was already done. There's 3.08 moles of glycerol, and water has 225 mils, which is 225 grams. Density of water is 1. So can I turn that into the number of moles? I need to know the molecular weight of water, which is 18.02 grams per mole. If after that calculation I actually have 12.5 moles of water and 3.08 moles of glycerol. So the mole fraction of water is the moles of water divided by the total moles is 0.8023. And this is the working number to put into Rouault's law. But sometimes when we talk about it, we express it as a percent. So it would be 80% or 80.23%. So if I do the actual calculation, I put in the decimal number. I multiply it by the original vapor pressure of water, multiply those together, and you would actually drop the vapor pressure down to 74.2 millimeters of mercury. And as it describes right here, it's 80% of the original. What happens when you do the same experiment, pressure gauges out here, and you figure out, hey, how does the pressure change when you have water mixed with methanol? And just to keep it consistent, we're going to do 3.08 moles of methanol, just so you can look at the same scenario. And if you added 3.08 moles of methanol, it would actually take a lot less of the methanol, because methanol is fairly light compared to glycerol. And you'll need to know the original vapor pressure of pure water, which is 92.5. But methanol is a little higher, it's 93.5 millimeters of mercury. So now let's start using Rouault's law, and this is where components come in handy. For the water, we just did it. 74.2 millimeters of mercury. Once again, stop and process what happened here. It's a colligative property. So the fact that it's methanol versus it being glycerol or anything else, or sodium chloride or anything, if the the dissolved components contribute the same number of moles, it's going to have the same effect on the vapor pressure. So no change in the vapor pressure or partial pressure of water is the way you would say that. But methanol itself also vaporizes, and it's easy to find the mole fraction because there's only two components. We just do the easy math here. 1 minus 0.8023. In other words, 20% of the vapor pressure is from methanol. We take it times that original vapor pressure of methanol, or the vapor pressure of pure methanol, and you get another contribution of 18.5 millimeters of mercury from methanol. And if you sum these up together, that would be the pressure total over the headspace. Partial pressures are right here, pressure total in the headspace. And once again, these follow Dalton's laws of partial pressure as well. So that's the number of moles that are sitting up there, and the percent by volume that's sitting up there in the headspace as well. Okay, vapor pressure change. Now this is a good example of using vapor pressure that we've looked at that for one calculation, but this is how we use it a lot in the lab, or you use it in refineries. Whenever you go by a refinery where they're splitting, jet fuel and gasoline and diesel and leaving road tar behind and all that stuff. How does that work? So let's walk our way through this calculation. It's all based on the same Raoult's law, where basically you're looking at the pressure of and I would say the components, but we're going to talk about the solvent. We'll call it solvent right here, but basically it's the same formula for components. So if I took a half a mole of benzene, here's the pure vapor pressure. I mix it with half a mole of toluene, and there's that pure vapor pressure. What is the partial pressure of each component, the percentage of each gas in the headspace, and the total vapor pressure in the headspace? And so just once again, I remind you that the pressure total is the pressures of each partial component. That's from Dalton's law. Okay, so now we're going to do this calculation. The pressure contributed by benzene is the mole fraction. So this is simple. It's 50-50. That makes it simple, times its original vapor pressure. So now here's the new vapor pressure in the headspace. The total is, these combined together, 61.8 torr. So if I took the new percentages that are in the headspace, it would be the partial pressure of benzene divided by the total, and the partial pressure of toluene divided by the total. And so in the headspace, it's no longer 50-50, but it's 77-23. And look which got the larger percentage, the one that has the higher vapor pressure. And that makes sense. It's more volatile. And what's the new mole fraction in the headspace? The same amount. That's what Dalton's law of partial pressure teaches us. So if you condense this back down, if you took whatever was in the headspace and condensed it back down, what would the new mole fraction be? Well, it would be 77-23, the same that was in the headspace. All right, so let me show you how this works. I'm going to just set this up, a little diagram over here. Here's how it started. It was 50-50, right? And then those both vaporize. But the higher vapor pressure one, the benzene, more of it went into the headspace. So now if I could get another condensing chamber over here, and I could just pipe that stuff over here, all right, and then just seal this thing off, and now let's recondense this. It's going to be in this new percentage where the higher vapor pressure came out higher, 77-23%, right? And that you could now do that again and again and again, and every time you'd have this differential that would start to build up. So let's do it one more time, just to kind of get the idea across. So now we get to the new headspace. It's 77%, 23%, and now you take it times this original vapor pressure. Now it goes up to 73 torr and 6.5 torr. You add those together, it gets 79.5. Now you would increase it to 92% benzene, 8% toluene. So you could imagine the next time it's going to be even bigger and bigger. So each fraction, each time you go through one of these vaporization and recondensing phases, you get it more pure for the higher vapor pressure solvent. So the more volatile component purifies through multiple distillations. So here's a diagram of a fractional distillation column that might be used in industry, and what you see is that steam actually generates all the different energies needed to vaporize, but on each vaporization there's a vaporization recondensing level. Okay, and as these recondense, after you've gone up a few times, you basically can start getting out the components because they are fractionally preferred as you get higher and higher in the column. And as you get to the very top, you get the things that fraction with the highest vapor pressure, gasoline. You work your way down, things with the lower boiling point, kerosene, things with a even lower boiling point, heating oil, lubricating oils, and then you get down to crude oils, and what's left over at the bottom that doesn't really vaporize at all is the stuff like asphalt and tar. And in the lab we use variations of the same thing, where we use a fractionating column where you basically just pack it with beads, so it physically boils and recondenses and works its way up, so the very high vapor pressure solvents are isolated off first. And sometimes what we do with that is we just take a fraction, collect it, and then raise the temperature and get the next fraction, collect it, and raise the temperature. So I hope this has helped you understand the solubility and colligative properties. And these three films together, they're long, but I hope you put those together and look at them all together to understand the overall principles for all of these. You'll look at actually the units that are associated with each. And then in this video, we really dove into the actual calculations.